My name is Marcin Parafiniuk. I'm a low-level programmer. I deal mostly in C, C++, a little bit in Rust. I do driver development for SmartNICs. And low-level networking in general. Okay, I can see that works. Yes. Thank you, Adam. Okay.
Yep, I'm glad that you can hear us now. So I'm Lukas Krzonowski, and I'm senior software developer with CodiLime. I code mostly in C and C++, but in the low-level stuff mostly. And I'm a huge enthusiast of Rust.
Okay, so today we're going to talk about Rust and C in networking. First, we're going to talk generally about Rust, then about applications of Rust in networking, and then specifically about Rust and C, about the bindings, how you can connect to C from Rust, then how you can integrate Rust with DPDK, which is obviously the biggest C networking library, and about the example that we have prepared for this. We have written a little application that uses Rust with DPDK, and we have run a performance test on that. And at the end, there's going to be a Q&A session. Please submit your questions during the presentation to the chat. And then at the end of the presentation, we're going to scroll back and answer the questions. Okay. So about Rust.
Yep. So Rust recently have been gaining a lot of popularity, mostly because it's very fast, even with all the features it offers, and performance is comparable to that of C and C++. So that's why it's such a good choice in the areas like low level, where C and C++ would be usually the first choice. Although being really fast, Rust is still pretty young language, so there might be a problem with libraries. It's hard to compete with 50 years of libraries development for C. Some libraries in pure Rust might be missing, or just not well maintained, or not mature enough for production. And that's where another advantage of Rust comes in. It can be integrated with existing C, C++ code that's well-known and well-tested.
What is very cool about Rust is that it offers memory and thread safety features. What I mean here is that the Rust compiler analyzes the code pretty well and aims to prevent all of the potential segmentation faults and memory leaks. It is literally impossible in pure Rust to make a segmentation fault or a memory leak bug, because the compiler checks all of that in compile time. So that prevents a lot of bugs, especially the thread bugs, the races bugs, that can be, it can take literally weeks to debug that. So, and Rust catches all of that in compile time. And what is also a nice addition is that it's the most loved programming language. It ranks consistently since, 7 years, right?
7 years.
7 years as the most loved programming language in Stack Overflow surveys. As we know, it can be sometimes difficult to come by programmers. So this is definitely something that's going to appeal to low-level developers, C and C++. All of these people want to code in Rust. I also code mostly in C++. I would like to move to Rust as well. Okay, so about Rust in networking. I would say that Rust is somewhat introduced to the networking field, but not really that well. We have a complete network stack. It's called small TCP. You can route packets, you can do everything. The basic things, like Ethernet and UDP and IP4 and IP6, stuff like that. What is cool about small TCP is that it can work without a kernel. It's also designed for embedded solutions. There's many packet manipulation libraries. Many of them are also rather widely downloaded. For instance, like 50,000 downloads, I think I've seen. But they only support basic protocols that I have mentioned, which is Ethernet, IP4, IP6, TCP, UDP. there is little support for skeleton technologies that might be used in ISPs. For instance, VXLAN and MPLS. That's something that would have to be introduced and also tested. Okay, so about binding Rust to C. Rust can natively call C libraries. It's a feature of the language. However, there is a significant difficulty here. C and Rust manage memory quite differently. In C, you just malloc and free the memory whenever and however you want. C doesn't care about this, doesn't check anything. And you can just do it. This is also where C's speed comes from, right? Because like it's very, very simple. However, Rust, as I have mentioned before, checks everything. Rust prevents all of memory leaks and segmentation faults. So to do that, Rust needs to know all of the lifetimes of the objects, needs to control for that. And when we have objects that are allocated in C, we do not know what their lifetimes are. So we need to somehow tell that to the Rust compiler. So to do that, we usually, when we write a wrapper, we have two layers. The first layer is usually trivial. It's auto-generated often. You can just run an external program. It's gonna just give you the code for free. But it doesn't do anything smart. And the second layer, this is where the real difficulty comes in. We have to express C libraries assumptions in Rust. So what that means is we have to tell Rust what the lifetimes are when the objects relate to each other in the memory. So which objects needs to be alive when, or rather when other objects are using them. So as an example, we have here a little bit of OpenSSL code. The highlighted portions of the code are the ones where we're using direct references to the C code, right? We have the unsafe blocks that relate directly to C methods, and a native pointer. And in OpenSSL, there is a global context. It needs to be alive all the time when we're using the OpenSSL library. So so we need to tell Rust library, tell the Rust compiler that the context needs to be alive for the whole time. So we need to initialize that using the unsafe methods and then drop it, which is to free it. And we do it in such a manner that we can never use the OpenSSL methods when the context is not initialized. If we will write this correctly, it will be literally impossible to make this mistake. And I've seen these kind of mistakes being made quite often. So this is a nice feature that Rust gives us. There is no threading support for native pointers by default. We need to tell Rust that it's okay to enable threading traits. We can move the pointers or share them from different threads. But this is only if we know for sure that we can do it. If we have read the documentation, we have understood the code, we know that it's okay for the pointers to be accessed or moved from different threads. We enable that for Rust, and only then we can also do that from Rust. This is also how we express the assumptions that C makes about its memory to the Rust compiler. We need to express lifetime dependencies of C libraries in Rust. In this slide, we have a little bit of a more complicated example. This is also OpenSSL. As I have mentioned, OpenSSL needs the global context to be present and alive for all the operations to be made. However, there is also another structure called Cypher. and Cypher can only be used as long as its global context is also alive. So here we also have to tell Rust that, and we do this using the phantom data construct. It doesn't really matter what it does in technical details, but what it tells Rust is that Cypher needs to be alive this instance of Cypher needs to be alive the whole time, or rather, that the context is needed for the Cypher to work. So Rust will prevent any calls that use the Cypher instance when the context is not alive. And that prevents bugs that could have been otherwise made. In C, you could just call anything anytime you want, and there's gonna be some weird errors, and that's not okay. That's something that can be prevented using Rust. What is also nice in Rust is that we can wrap return errors in a result monad, result structure. I mean, that really seems like a trivial and everyday thing, but like managing errors is crucial. I've seen many bugs being made and fixed because of wrong error handling. So like in Rust forces you to deal with the errors somehow. If you ignore them, you have to ignore them explicitly, which also like helps to debug the code and manage where the errors are handled. In Rust, we also have resource acquisition is initialization. So there are no like uninitialized structures or something like that would also introduce like undefined state or something that would introduce bugs. What is also worth mentioning is that string management is different in Rust and in C. In C, it's a series of bytes ended with a 0, and in Rust, it's a buffer that has a length and a content. So the point is that you have to convert the strings from the C format to the Rust format when you interface with C libraries, which is also something to keep in mind, but it's not a big deal. It's just something to remember. If done correctly, all of this will just work. Obviously, the initial migration will take some time, but it's a one-time investment. After we write the first layer wrapper and the second layer wrapper, we express of all the libraries assumptions, all the C assumptions in Rust. This is we can use all the Rust features and all the guarantees that Rust gives us also with the C libraries. So that will prevent or catch many bugs at compilation stage. And what the goal is to have the program's correctness basically proven by the compiler. So if the program compiles, we know for sure that it's not going to have any memory leaks, any seg faults, any threading issues, right? As long as we write the wrapper correctly, from that point, we can just continue with the development and have many, many bugs be prevented at compilation stage, which is very cool. Okay, now I would like to talk more about how we used Rust with DPDK. As I've mentioned, DPDK is probably the biggest, the most interesting networking C library. There's many projects using DPDK. There was already a first layer wrapper that we found, the one that's auto-generated, so we just took that. But we had to write the second layer wrapper, and we solved memory management and threading issues. And we also had to express some of the assumptions that DPDK makes to the Rust compiler. And if you wanted to continue the development of a DPDK application to manage more data, modify the packets, write a forwarder, write a router, or whatever, from this point, development would be easy. We would just use the wrapper that we have already created, and then we could just write everything else in Rust and have all the features that Rust gives us. So what we've done with Rust and DPDK, what you have on the right, this chart expresses the dependencies that the DPDK has for its structures. We have the abstraction layer, which is a kind of a global context, and then you have Ethernet devices that depend on the context, then you have queues that belong to specific Ethernet devices, and then you have RX and TX operations that you do on the queues, right? Receiving and transmitting. So we had to express all of these dependencies to make sure that, for instance, you cannot receive on an initialized queue, or that every queue belongs to an Ethernet devices, or that all the devices are alive as long as the queues are alive, all this stuff. All of these errors would be impossible to make in Rust. And because the chart is rather complicated, this is obviously just a subset of that. There's many dependencies in the DPDK library. It gets complicated. It just gets complex, and it's hard to keep track of what is alive when. So it's very convenient to have that taken care of by the compiler, and you don't have to keep that all in mind. So we've done the global context initialization, we've done the port queues initialization. Yes, I've talked about the dependency management. Also, the thread safety. What is important about this is that DPDK is designed in such a way that every queue can only work on one core, on one thread, and the RX and TX can be done only from this one specific thread. So that's something that you also have to keep in mind when you write in C. But in Rust, the program will not compile if you try to transmit or receive from a different thread than the one that the queue was created on. We also have to keep we also have to keep the DPDK's LCore assumptions. DPDK has its own idea about threads. It's called LCores. They have their own threads, and these LCores. First off, they keep that assumption about the queues that are just one-threaded, and another assumption is that that each and every LCore has its own hardware thread, its own CPU thread. So we express those things in Rust to make sure that there is going to be no errors in using DPDK structures. However, we have not used actual LCores. We also could have used actual LCores and run our Rust code on the DPDK LCore structure, but that would only improve caching, I believe. DPDK has well-optimized caching, idea about what happens if a thread accesses memory from different NUMA nodes or different places in memory. But we just did not need that, and it would take more time, so we decided to move on. We also have tested a few packet content modification libraries, and we chose the one that had the best performance. And it turned out that we can modify packet content, the source and destination address in Ethernet frames, in just 2 to 3 nanoseconds, which is basically as fast as it gets. We have also read the assembly generated from Rust there, and it was just a few instructions. So it was very well optimized and very fast.
Yes, so we created those bindings for DPDK, and we wanted to test them. DPDK itself ships with several example apps, and one of them is a very simple layer 2 forwarder. So what we did, we wrote the same functionality in Rust using our bindings to compare performance between C and Rust. We had our custom setup. We used T-Rex traffic generator and 2 Intel 25 gigabit cards. This is the topology of our setup. So we made sure, we were running the forwarder on a single bare metal server. So we made sure that DPDK and traffic generator are running on a separate NUMA nodes. So shared resources like memory and cache would not impact performance. One CPU was T-Rex traffic generator running on 16 cores. On the other CPU was DPDK forwarder. And in infinite loop, we were parsing bursts of 32 packets, up to 32 packets. And we were just swapping source and destination MAC addresses and just sending it back. So as simple as it gets. To compare performance, we run regular RFC 2544 tests. And as we can see, throughput was almost exactly the same. So there is no significant difference visible on the charts. What's worth to mention that above packet size of 250 bytes, we actually hit maximum bandwidth of the network card. So hardware was actually the limit at this point. But below that level, performance of both applications, like in Rust and C, were exactly the same. We also tested latency and jitter. Due to the measurement technique we used, those results are actually almost the same. So it all falls way under measurement error. So there is also no visible difference. To show difference in throughput between Rust and C, this is the chart that shows the difference between those two. What we can see, the chart flats out after certain size because of the hardware limit, but below that, we can actually that Rust is slightly faster. So there is some optimization happening that in a no packet loss scenario, Rust is slightly faster, but the difference is actually very minimal. It's 100 packets, and the overall throughput was in a range of 20 million plus packets, way above 20 million packets per second. So 100 or 200 packets is not much of a difference. To expose any performance differences, we did an overload test. So in this scenario, we used the smallest packet of 77 bytes, and test lasted for 30 seconds. T-Rex was tuned up to achieve packet loss, and it was actually pretty big, so it's not a real-world application. That's not the scenario that would be wanted in any deployment. But of over 1 billion packets transmitted during that test, only about 60% was sent back from forwarder, which means drop was about 40%. And it exposed that Rust in such scenario performs slightly worse. So end result was almost 1% worse for Rust. It's not much, but it's worth mentioning that in this particular setup, Rust did not perform as good as C. What's also worth to mention that there was way better performance on the C side in handling received packets. So we were using single RX and TX queues and single core, single thread. So this means that's why we had such high packet drop, but C was better in handling receiving of packets. It did not impact the end result. So a packet drop on TX queue was way higher on C. That's why both applications ended up with almost 60% of packets sent back. But C was handling way better polling packets from the RX queue. Last column here, it's average burst size. So due to the way how DPDK polls packets from the network card, we cannot really measure CPU usage. It's always going to be around 100% because it's infinite loop with constant polling of from the queue. It's just the DPDK way. It's due to higher performance, but it's hard to measure CPU load. So this is kind of approximation. we can see that with 32 packets burst, Rust was always, average burst size was the maximum. So there was no free CPU time at all. Like the queue was always larger than 32 packets, while C was able to empty the queue most of the times. So the average burst size is slightly above 24. It's hard to compare these results, but it shows that C is way better in handling packets from RxQ. Yep. So.
Okay. To sum up, Rust is much less error-prone and performs thorough checks and analysis on the code. Rust basically aims to prove that the program is correct, and it prevents a lot of bugs. Especially the memory and threading bugs that are especially difficult to find and debug in production. I've seen these kind of bugs take weeks to being found and fixed. So I think it's very cool to have that just prevented on the compilation stage. Rust requires more skilled developers, however, it is attractive to programmers. Yeah, I mean, it does require some kind of background in low-level stuff, in C and C++. What Rust does is basically forces you to use the good practices from C++. So it's very nice to know what they are at first. If you just try to force Rust on somebody who has just like dealt with Python or JavaScript before, it's probably not going to work as well. But it is attractive to programmers, and everyone that's like, I mean, it's a strong opinion. It is just my personal opinion, but like everyone that's been coding in C or C++ is going to really like Rust, because Rust does a lot of stuff well that C and C++ does like not that well. Okay, binding from C is possible, however, it is a sizable one-time investment. Yeah, I mean, as we've seen, it's a project in and of itself, basically, right? To like write all of these wrappers, you know, to express all of these dependencies, all of these assumptions that libraries in C make. You have to codify that in Rust. You have to like express that in Rust. So that's a lot of effort. But from that point on, when you continue development in just in Rust, in pure Rust, and then you have all of the Rust features, all of the bug prevention, all of the analysis, and you never have to like look back at that, right? Like you just write this wrapper once the wrapper to DPDK, for instance, or some other library that you need, and then you can just keep moving on and have a lot of time be spared. You know, like a lot of development is spared because you don't need to do this, because you don't need to fix bugs.
Yep, so we were able to successfully integrate Rust with DPDK. We've shown a working example, and there still might be some work required, but anyone can just take that code. Do not worry about DPDK assumptions, because they are already verified by Rust compiler. And with all the benefits of Rust, performance is comparable to that of C, which is great, actually. Yep. So.
Okay, so that's everything from our side.
Maybe you have some questions, so feel free to post it in the chat.
Yeah, we're gonna give you like a minute or two and see if any questions are going to come up, and we'll be glad to answer them. Okay, we have two questions. I'm gonna take that. How memory safety is secured? Is there any garbage collector? There is no garbage collector, which is a good thing because a garbage collector has a performance penalty that can be sizable. For instance, in Java, like tuning the garbage collector is an art in of itself. No, what Rust does is Rust tracks all of the memory and makes sure that all of the memory is freed when it's just not needed anymore. It just drops that when the lifetime is over. It usually is a zero cost optimization, which means that it basically boils down to the fact that free is called in the correct time after being made sure that no other structures that are alive at this point to this memory that's being freed. However, as we've seen on the summary slide or on the previous slide, on the overload slide, sometimes the drops also can introduce a little bit of a performance penalty. However, this can usually be optimized. So like we didn't do it because the actual performance of the whole solution was satisfying. We only had like a 1% difference. But if we wanted to fix that 15% difference from the reading from the queue, that probably would have also been possible. We would just have to spend some more time on that. Okay, another question. You have mentioned multi-CP. Is it already in use in any commercial project? I'm not sure. However, there's a company behind that.
Yes, we actually don't know, but it's popular and it's hard to tell. Like usually companies do not share that stuff. We didn't find any, but there is someone behind it, so they are probably using it.
Yeah. There's an actual company putting their time and effort into multi-CP. So that's a cool thing. Okay, another question. So from development perspective, you want to take that?
Yeah, so from development perspective, C has still better performance. So would be the biggest benefit to transitioning to Rust is saving support time. Example, less bugs that can be caught during compilation. Well, yes, I would argue with this better performance because like we did proof of concept and it's probably still possible to squeeze more performance out of these bindings. So in pure Rust, library can be as fast or maybe faster than C, C++. So from the language perspective, there is no such a difference. But with bindings, you need to remember about everything. So maybe there is a way to get rid of the problem that we encountered in overload test. We have some suspicions what might be causing that, but it was just proof of concept. So we didn't put much time and effort into that. Support time, definitely. Actually, it's not only less time in saving support time. Not only time, but it's probably faster to just solve some issues during compilation time. Like if there is a bug somewhere deep in the code in C or C++, it can take weeks to find. With Rust, we are notified right away. So actually, that's like very advanced static analysis of the code. That Rust pinpoints you location where there might be a problem. Actually, it's not always the case that depending on how you use your code, it might or might not be the problem, but Rust will just warn you, and in this case, the warning doesn't allow you to proceed further. So you have to write it correctly, like the way that C and C++ should be written as well. You need to check some stuff, and if you don't, you cannot proceed with Rust. So pure Rust code, well written, should be as fast as C, C++, but at the same time, you can be more. You as a developer can feel more confident that it will work correctly, and there are some memory management, especially bugs or some threading issues, which is very easy to make with C or C++. Yeah.
Yeah,
Something to add?
Yeah, it's pretty much everything. Okay, so maybe another minute or two.
Okay, I guess if there are no further questions, you can always ask them on YouTube, and we will try to monitor the video. It will be available later to watch on YouTube, and we will also monitor the comments, so any further questions are welcome.
Yeah.
Thank you.
So that's everything from us. Thank you very much for coming to our little webinar, and have a good day. Thanks for watching.